Hello and welcome to the final lecture on urban economics for 2020. It's a great pleasure to welcome Esteban Rossi-Hansberg from Princeton, who's going to talk about the dynamics in spatial economics.
So thank you very much for organizing this set of lectures. I think it's a great idea to do so. And thank you very much for including me in this fantastic lineup. So, I think the Urban Economic Association has done a great job in promoting urban economics, and particularly recently with all these events, with the dynamism of Don Davis, and now with Daniel taking over. I think this has really been great for the field. So congratulations to both of them. And again, thanks for including me. So I'm going to talk about dynamics in spatial economics. And the idea is, well, you've heard essentially about, in all the different previous lectures, you heard about different topics, different dimensions in which space matters. One that has been, a little bit relegated in all those talks is dynamics, is the fact that, whatever happens in particular location affects the evolution of the economy. And so what I'm going to try to address today is, how do we think about dynamics in spatial context, and, what can we do so far, and what is missing, and in general, how, what's the agenda looking forward. And, so I'll try to introduce the topic in somewhat of a general way to try to organize a little bit the ideas around the topic. And then I'll focus in on one particular dynamic framework in order to have something concrete to show you, and show you a little bit of some of the mechanics of one particular model here. So, so the starting point, I guess, is that when you look at growth of GDP per capita across space, it varies dramatically across regions. And of course, that's not surprising. You can think about why it varies. Examples abound, but you can think about local shocks, for example, weather shocks. I'm going to talk about, some applications of dynamics to think about climate change. So you can think about climate shocks. You can think about differences in innovation across space. So, if someone invents the light bulb in New Jersey, suddenly you have a whole industry emerging in New Jersey. Or, if California has some good, or Northern California has some good environment to foster innovation, then, Silicon Valley becomes an engine of growth of that region, but also of the economy as a whole. You can think about factor mobility, local investments and adjustment costs, how local shocks then, imply that people are going to move across locations, and that in turn is going to affect local growth. You can think about changes in institutions, as in the work of Tom Holmes, for example, the right to work laws, and kind of the effect that had in growing the South relative to some of the Midwestern locations. In general, we can think about many reasons why, growth rates across locations vary, but in general, the data suggests that, they vary a lot. And not only that, but even within countries, even in kind of relatively homogeneous environments within a country, we see a lot of variation in these growth rates. And so, the natural questions, or our natural question we want to ask is the distribution of economic activity, how things are located in space, important for growth? What is the role of agglomeration and cities in that sense for growth? And what are the growth consequences of spatial frictions that I'll talk a lot about, like the ability to move people, things, factors, etc. in space. And then you can, of course, turn these around and also ask, well, how does local growth and aggregate growth affect the distribution of economic activity and affect, spatial inequality? And so there's I'm not going to really address inequality in particular here, but it does, but growth is naturally related to the fact that some regions are going to end up with more people and perhaps richer than others. And so just as an example, I have the map of the US here, obviously different states in the US, and what I plotted here in different colors is the annualized GDP growth rate between 2002 and 2007. This comes from a paper with Lorenzo Caliendo, Pierre Sartre, and Fernando Parro in 2018. And so there's an annualized GDP growth rate. And so you can see, the differences even within the United States, right? So Michigan here, essentially didn't grow during that period, while Oregon, grew at an annualized rate of 8.6%. So these are huge differences, right? So they accumulate very fast over time if you keep them consistently. I mean, if one particular place has a consistently higher growth rate than another. Now, of course, what are the reasons for these big differences in growth rates? Well, an important part of it is that, factors were moving to Oregon relative to Michigan. And so, there's more people there, there's more capital there, etc. And as a result of that location is growing. So this is GDP, this is not GDP per capita. We can alternatively say, well, let's control for all those factors, right? And now let's look at TFP. So some measure of productivity growth or growth in TFP, productivity growth in the state once you control for the fact that labor and capital and all of those factors are also moving. And then the differences are smaller. So now Michigan grew at 1.1%, while Oregon was growing at 2.5%, but they're still quite significant, right? And these are now differences in actual productivity. So productivity growth across places in the United States still varies substantially. And now, I chose this example of Michigan and Oregon before, but of course, there's even more extreme examples when you look at the annualized growth in TFP, for example, between New Mexico here and Oregon, as we chose before. And so, these differences in TFP growth are very important. And so we want to try to think about, how come we see some of these differences in productivity growth that go beyond the fact that factors are moving across locations. Now, when you think about cities and growth, there is in some sense like a basic tension, a basic confrontation. Why is that? Because cities, as we've heard repeatedly over these different talks and these different weeks, cities require the existence of scale economies. They are evidence, in some sense, of the existence of scale economies. The fact that agglomerating, is useful. Doubling the factors that you can double, the factors that can be reproduced, has to more than double output. Right? So those agglomeration effects are essential to think about cities and are kind of at the cornerstone of pretty much all theories of cities. But when you think about growth, right, the most important fact in the growth literature is balanced growth. Is the fact that when you look at very long-term growth over very long periods, the growth rate is not exploding, is not going to zero, it's staying at around, say, 2% 2% in terms of in per capita terms. And so, there's a little tension which says, well, on one hand, there's these economies of scale where if we pile up more resources in one particular location, we are getting more and more. On the other hand, balanced growth says, well, that cannot happen because as the economy, grows and gets bigger, we don't see an acceleration in growth. And so that tension, it's there. And so the question is, how do we reconcile that tension? And so this balanced growth argument was famously made by Jones. And what that requires essentially is that you need in the aggregate linear technologies. So for cities, you need increasing returns to scale. But for growth and for balanced growth, you need constant returns to scale. And so that's the tension, right? And so how do you solve that tension? And for, everyone that has kind of in some sense been paying attention to this lecture, maybe the answer is obvious. Once the force that allows or solves that tension, allows us to solve the tension is congestion. Is the fact that, those increasing returns, those scale economies are balanced by congestion. And as they are balanced by congestion, they lead to the distribution of economic activity, right? They determine the distribution of economic activity. And so in that sense, it is the distribution of economic activity what makes the economy go from the local increasing returns or scale economies to the aggregate linearity in the production function, which leads to balanced growth. And so in that sense, the distribution of economic activity is essential to think about growth. It's essential, it's an essential component of growth, and is determined exactly by the balance that determines and that leads to the linearity in the aggregate production function. And so that's an argument, that we made with Mark Wright in a paper in 2007. So if you want to kind of the details of how that aggregation works, you can see it there. But the argument is general. You need that the distribution of economic activity is the force that exactly balances those increasing returns. And in that sense, it is essential to think about growth. And this is something that, in the mechanics of economic development in '88, Lucas recognized, cities as an important force or the role of agglomeration in cities as an important source for growth. But it has to happen through this form of aggregation and through the kind of the balancing that leads to the distribution of economic activity. And then, of course, the local characteristics, the specific characteristics of the different locations are going to determine how much each region produces and how big each region is and relative to other regions. And so how individual regions are going to grow. And so the economy is going to grow by increasing the size of particular cities, but it's also very importantly, and this is essential for that aggregate linearity, going to grow by replicating these cities in space, by adding more locations in which we are producing. And the ability to do that is essential to generate that distribution of economic activity and the linearity in aggregate growth. And so, so again, these two concepts are very much tied together. Now, when I say, well, let's study the dynamics in space, why do we want to do that? Or what's the basic goal? Even though, what we said is like the distribution of economic activity is essential to think about growth, why do we want a careful model, and why do we want to kind of have a theory of the way that happens? Well, one important reason is that we want to think about the effect that spatial frictions and spatial shocks have on those growth rates. Can changes in spatial frictions and can particular spatial shocks affect the growth rate of these economies? And so, that's an important question, because in some sense it tells us, well, if we change trade barriers, can we generate more growth? If we change migration frictions, can we generate more growth? Or is it simply going to be, static reallocation effects? Or are we only going to get like static reallocation effects? And of course, this is important, because if you manage to, get growth effects, if in fact those spatial frictions and changes in those spatial frictions lead to growth effects, then the welfare implications of policies that affect the spatial frictions, so that, lead to particular spatial shocks, can have very long-lasting and large effects compared to purely reallocative type of impact. So we want to try to study the effect of these spatial frictions. And so what type of model do we want? Can we just simply use the type of models that I was talking about before, say in that paper with Mark Wright? Well, the reason those are in some sense are not sufficient, and the reason why all the previous theories of systems of cities and growth in some sense are not sufficient to think about spatial frictions and the role of spatial frictions for growth, is that they don't have geographically ordered space. And so what do I mean by that? But what I mean by that is that locations are not linked in their geography. And so in particular, there is no cost that depends on where they are. There's no cost or benefit that depends on where they are in the map in particular. Now, it's very easy to incorporate geographic order space. You just need costs, for example, that depend on distance, that's sufficient to make the map matter. But in the classic theories of systems and cities and growth, like the wonderful paper by Black and Henderson, the paper by Gabex on the size distribution of cities, the paper that I mentioned before with Mark Wright, and all those papers don't have geographically ordered space. They have some growth, but they don't have geographically ordered space. There's of course a very large literature in trade and growth that also that does have geographically ordered space, because of course has trade, and trade that depends, or the trade costs that depend on distance in particular. And so the work of Grossman and Heldman, Eaton, Kortum, and Niemann, and recently Ricardo Reyes Heroles in a beautiful paper on trade costs and global imbalances, have made big advances in thinking about dynamic models of trade. But in general, those frameworks don't have labor mobility, and so they don't allow for agglomeration to play a big role in affecting growth rates, or no role in affecting growth rates, in the sense that labor is not mobile in space. And in many cases, we're talking about a few countries, not really, thousands of locations when we think about the spatial frameworks, like what Steve was talking about a few weeks ago, or what Dave was talking a couple of weeks ago, etc. So, there's something to do. We want to incorporate dynamics into a model with geographically ordered space in order to think about the growth impact of spatial frictions. Now, when do spatial frictions have growth effects or dynamic effects? Let me say it like that, rather than just level effects. Well, two elements seem important. The first one is we can have factor adjustment costs, so that if you hit one region with a shock, people move maybe there, but not immediately because there's frictions. And so that leads to adjustment costs and adjustment cost dynamics. And so that, of course, can affect the overall present discounted costs or benefits of particular shocks. So that type of adjustment cost can be important. And the other is local investments. If agglomeration leads individuals, firms, or agents to invest differently as a result of the fact that they are in a particular location, then the distribution of economic activity directly is going to impact growth, and it's going to have long-term growth effects. And so we want frameworks that have one or the other. Now, this turns out to be a pretty hard problem, and that's perhaps why this is the part of the spatial world that has been a little bit underdeveloped. And why is that? Because we need models that where agents are making intertemporal decisions across locations. And so if these agents are forward-looking, if they need to predict the implications of their actions in the future. Now, of course, their actions in turn affect the economy in the future, right? And therefore affect their own evaluation of what they should do, right? And so that's the classic problem in economics, in dynamic models of the economy. And of course, all of macro is based essentially on trying to solve these type of problems. And so we know a lot about how to solve these problems. But when you talk about space, there's some singularities in some sense that are a little bit different than when you think about macro problems. Why? Well, the first one is, of course, that you have the spatial dimension. And so agents, need to predict what's going to happen in all locations, not in the location where they are, right? And how their actions affect, all locations, not only the location where they are. So that's the first issue. But the second is that in contrast with macro problems, agents not only care about some moment of the distribution of states in the future. Like, for example, in macro, it's very typical to think, well, agents care about the interest rate, the future interest rate. And so they need to predict the future interest rate. And the future interest rate may depend on some moment of the distribution of savings or capital holdings of the different agents in the economy, right? And so as long as I predict that one moment, right, I know everything I need to know about the future. And so everything at the end of the day is about, trying to create expectations about one particular price or several particular prices, etc. Now, in spatial economics, this is a little bit different. Well, first, because, what you need to predict is the whole distribution of location, or the future, the whole distribution of locations. That's one aspect. But perhaps the most important and nuanced aspect is that agents in a particular location, or firms in a particular location, care about the future in the different locations differently, depending on where they are, right? Why? Because I care more about locations that are close to me than locations that are far away from me, right? And so in some sense, the way I care about the distribution is different than someone, that is in San Francisco or in Zimbabwe cares about the distribution of economic activity in the world. And as a result of that, we need to carry and we need to create expectations about the whole distribution. And so that in general is a very complicated problem. Now, there is a literature, Daniquois, Busekin et al., and Brock and Cepapadeas, the papers that I have listed there, that, address this problem in all its generality. They took out labor mobility, but they did incorporate the spatial capital allocation problem with diffusion. These are beautiful papers, very done by very serious mathematicians. I mean, economists, but that are technically very gifted. And they really, make a big attempt to crack this problem, but it is a hard problem. And, as Busekin shows in his paper, it's a problem that in that generality is what mathematicians call an ill-defined problem, in the sense that you cannot do what, we standardly do with macro models, which is, go to some steady state and then solve the problem backwards, because it leads to different types of bifurcations, etc. So this is all to say, the approach of let's just crack it with a big hammer, right, essentially hasn't really worked so far. And so, what do we as economists do when this happens? We simplify, right? So we simplify the problem. And so there's two main simplifications that I want to talk about. These two simplifications, are both useful for different aspects of this problem. The first simplification is the one that I'm going to put under the label factor location does not affect the future. So what does that mean? It means, that essentially we're going to take the evolution of the fundamentals of the economy as given, and then think about the allocation of people. And so there's no firm capital or innovation investments. There's agents consume what they earn, so there's no consumption saving decisions. But, and this is the beauty of it, there's forward-looking agents that are making dynamic decisions depending on what will happen in the future. And so that's great. And the basic strategy there is use this kind of renewal action logic in order to solve the dynamic discrete choice problem. And so, or as Caliendo, Dworkin, and Parro in a famous paper they do this, dynamic hat algebra, where you can essentially cancel out some parts of the equilibrium problem that allow you to solve the dynamic problem. But the basic logic is kind of essentially this renewal action solution strategy. And so what's great about this approach is that it has anticipatory effects. So what do we mean by that? What we mean by that is that if something happens in the future, right, agents are going to react today. They're going to take that into account, and they're going to adjust to whatever what will happen in the future that they are foreseeing that will happen. And so in that sense, they are anticipating what will happen, and they're reacting today, understanding that this thing is going to happen in the future. Another important, or great advantage of this is that, whenever you have a shock, Katrina comes and destroys parts of New Orleans, people start moving and start reacting to it. But if it's costly, that's going to imply that there is a long-lasting dynamics, right, as a result of that shock. And so if you want to kind of try to understand those short-term dynamic effects, how people, adjust progressively to particular shocks, this is fantastic, right? Because it gives you the whole path, and it tells you, it allows, and it's the full dynamic path that allows you to evaluate these problems in some sense correctly, taking into account how the economy is going to evolve as a result of these shocks. And so, a big paper there is Artok et al. In 2010 with McLaren in the AER, then the Caliendo, Dworkin, and Parro paper that I talked about, where they study this China shock and the effect, kind of the dynamic effects of the China shock, how, the entry of China into the world trade affected different regions in the United States, and in particular how people then reacted and move as a result of that, and kind of what are the dynamic implications of that. Or Claire's wonderful paper on coastal flooding, and how coastal flooding will make certain infrastructure investment better or worse depending on where they are and how susceptible they are to the future flooding that will happen. Okay, so this is a great framework, and it's really nice if what you want to analyze is anticipatory effects, or whether if you want to think about this short term, or short is a little bit of a in the eye of the beholder, I guess. But you know, the dynamics, I should say, that result from this particular shock. But you know, eventually the economy adjusts here, and then there's no more growth effects, or there's no more you know, implications of the particular shock that are dynamic, that are changing the economy over time. So if you're interested in investments, or if you're interested in the consumption savings decisions, this is not the framework. It doesn't have those elements. But of course, that's not to take anything away from this. These are wonderful papers, and you should definitely read them all. If you want anticipatory effects, and if you want the dynamics of the shocks, this is the way to go. This is the absolute state of the art. The second simplification, it's a different simplification, is essentially making enough assumptions to make decisions effectively static, right? So this is essentially, you know, instead of making agents need to predict the future, right? So we can say, well, they don't want to predict the future because they don't care about the future, say they are myopic, or because they're gonna die, right away. That's like in the paper that Dave Donaldson presented before. There were dynamics, but you know, people didn't have to predict the future because they moved, they lived there, and then they died, and there was no future effect of that. Or you know, somehow they don't care about what's going to happen in the future. So you know, this is importantly not to be confused with not having dynamics. These are frameworks that are very much dynamics, and that can lead to very rich dynamics, because agents are still going to make decisions that affect the future. It's just that for whatever reason, they don't care about how they are affecting that future. And so one example of that is this paper that I have with Klaus Desmet in 2014, where we put enough structure there, in some sense, in order to allow for firms to invest in particular locations and improve their technology in particular locations, but without having the complicated forward-looking problem. And so how do we solve that? Well, firms are forward-looking, but because there's competition for land, and firms, and there's diffusion of technology, that competition for land, and because land is the only fixed factor, right? At the end of the day, all the rents of the augmented land, of the better land, because we invested there in the future, are gonna go to landowners. And because land is inelastic, right? That affects the future economy, but that leads to no profits for the firm from those investing in the future. It leads to profits today, but it doesn't lead to profits in the future. And so that again, you know, makes the decision effectively static. But of course, these firms do invest, and as a result of that investment, the economy changes. And so, so we introduced that in that paper in 2014, and then in 2018 we have a paper with David Nagy as well, where we put that into a model with realistic geography, mobility costs, trade costs, etc. And so that's the framework that I'm going to talk about today in some detail. Now, one key thing there, and I'll again talk a little bit more about that later, is you know that mobility costs are reversible. So you need that also to make the problem of the individual effectively static as well. So you can reverse the cost by kind of moving back, if you will, and I'll make that clear. And then you know this again can be used to or applied to different setups. We have a paper with many co-authors where we study coastal flooding in that framework too, and I'll talk a little bit about that as well. Then you know, David in his dissertation studied the impact, the long run impact of railroads in that world. Matt Deventhal studies the effect of the declining trade costs, and there's others. Elisa Giannoni has a beautiful paper that uses some of this also to think about convergence in the United States, and how convergence is different for different individuals with different skills. So there's a little literature there as well. So I'll go into this in a little bit more detail in a moment. So what is missing? What is missing from this? If we just classify things in these two big simplifications, if you will, these two big groups that again are used for different things. The first one is really used for anticipatory effects and these short-term dynamics. The other one is to think about spatial growth, right? And so why do we want to think about spatial growth, or why is that useful? Well, think about climate change. If you want to think about climate change, then you really need to think about, well, maybe developing some other parts of the world is going to be useful in the future. And so you want to allow for that type of effect. Now, one big thing that is missing from both sets of literature is that in both cases, the consumption savings decision, there's no consumption saving decision and there's no wealth accumulation. So agents are kind of hand to mouth. You pay them, they eat. They have no ability to save, and that doesn't matter at all. So in a paper with Adrian Bilal, we introduce a consumption saving decision in a dynamic model, and we show that actually matters a lot for how agents make location decisions, particularly in the presence of credit constraints. So if you cannot transfer resources across periods using the financial system, you will use your location to essentially do intertemporal transfers. And so that just illustrates how the consumption savings decision and bringing the consumption saving decisions into play in these spatial models can be quite important. More generally, there's many other dimensions that we could add and that have not really been added to growth frameworks, but that have been developed in dynamic frameworks. And this is just to give you a taste of it. I listed 4 wonderful job market papers this year. And so, always go where the young people are, right? That's where things are happening. And here are 4 people in the job market that produce these papers and add to dynamic frameworks different dimensions. So local unemployment in the case of Bilal, firm dynamics and firm entry in the case of Walsh, information frictions in the case of Porcher, and sorting and endogenous amenities in the case of Almagro. So all of these are dynamic frameworks. They all have some component that is dynamic. They don't have growth though. And so, there's an opportunity there. There's an exciting research agenda to bring some of those insights into models of growth. Okay, so that's what I'm going to say kind of broadly about the literature. Now I want to jump into a particular framework that is going to allow me to be a little bit more precise about some of these points. And so this is this paper. It's called The Geography of Development with David Nagy and Klaus Desmet. And so what this framework is it's a framework of the world. So we're going to try to model the world. And the world is going to be in a grid. And that grid is what I'm going to call a location. So this is an area of the world. In the application that I'll show you later, is going to be a cell that is 1 degree by 1 degree. So it's a particular cell. And so there's, as you can imagine, so that's about 100 kilometers by 100 kilometers. And so there's many of those cells in the world. And so every location, every cell in the world is going to have 3 characteristics. It's going to have some amenities. So this is how good it is to live in that particular location. It's going to have some productivity that is going to determine how good it is to produce in that location. And there's going to be some geography in the sense that these are going to be locations that are in a particular place in the map. And so trading with other locations is going to be costly. and it's going to depend on where these locations are. Okay, so each location is then going to have these firms, and these firms are going to produce and trade subject to transport costs. But very importantly, they're going to innovate, right? And by innovating, they're going to affect those levels of productivity at the location. Okay. And so that's what's going to lead to the dynamics in the model, the fact that there is this endogenous innovation by the local firms that is going to affect productivity. And so why is that? What's the kind of spatial component? Why is the spatial component here important? Because the way they're going to do these innovations, their motivation to innovate in a particular location is the fact that if I pay for that innovation, that allows me to trade and sell, if you will, or sell to everyone that is relatively close to me, right? Or sell more to everyone that is relatively close to me. So if I'm in a very dense location, I'm going to have lots of people to trade, right, with. My demand is going to be high. And because the innovation costs what it costs, in some sense, there's like a fixed component to that, that leads to a big market size effect. So if I have a big market, I want to innovate more. Why? Because once I innovate, I can use that innovation as many times as I want. Okay. And so that leads to these market size effects, which are going to imply that the distribution of economic activity is going to matter for growth. So in terms of, the literature, for those of you that know that, there's the famous framework by Allen and Arkolakis, where we're going to essentially use a version of that, which is obviously related also to the framework by Eaton and Kortum, the original quantitative trade paper. And we're going to allow for migrational restrictions on top of that. And then the dynamic part of the model is like what I was talking about before in the paper with Klaus Desmond. We're going to so where firms are going to get zero profits in the future because of land competition and or competition for land and technological diffusion. Okay, so before I go into the mechanics of the model, let me make one point that is going to be important to think about the way this model is going to behave, and more generally, the dynamic and spatial dynamics. The model is going to predict that the correlation between population density and income per capita increases with development. So places that are very dense, right, are going to be rich, right? But that are going to be rich and progressively richer as the economy develops. And so, in some sense, a sign of development in this world that I'm going to create with the model is the fact that this correlation is large. Okay. So what's the logic, or why is this important? Well, it's important because, I mean, if you think about it, initially, people, where do people, before an economy develops, where are people going to locate? Well, there's places where it's, easy to fish, and there's places where, it's nice to live, there's a good climate. And so, they're going to balance, production and amenities. They're going to choose a location. But suppose, some places are particularly nice, so there's a lot of people there, even if they are not super productive. But what's going to happen is that in those places where people agglomerated, say, because of amenities, because they have temperate weather, say, what's going to happen is that over time, the fact that people are there is going to imply that they're going to innovate, and the firms there are going to want to improve productivity in those locations. And so over time, right, there's going to be higher productivity in those locations. That's the endogenous investment part. And so that's going to lead to a higher correlation between population density and income per capita. And so this kind of evolution of that correlation is going to be essential. And that seems consistent with the evidence, at least in the cross-section that we see in this data for one-by-one cells in the world. So let me show you this briefly. So if I take the GEcon, so we're going to use this data that Nordhaus put together at Yale that is at this 1 degree by 1 degree cell level, and that gives you population, it gives you real income per capita, and so you can take the correlation across cells in the world, and if you do that, that correlation is minus 0.38. So what is that telling you? It's telling you, the places that are very dense at that level, at that 1 degree by 1 degree cell level, the places that are very dense are not the richest places in the world, right? That correlation is negative. Now then, if you break down by countries, etc., and within countries, you can make that positive. So for example, the weighted average across cells within countries is positive, but small. So that's about 0.1. Now, if I divide the world into the poorest cells and the richest cells, so the richest cells I'm going to interpret as having gone through that process of development more, or at least modern economic development more than the poorest cells. If you see that, in fact the correlation is quite a bit larger, right? And if you kind of look at continents, for example, look at the correlation across continents, the richest continents, the continents that have gone through development have correlations that are much larger, or in general larger than some of the poorest continents. So that seems to be the case. You can go more micro at the zip code level or the city level, and again break down zip codes or counties by the level of GDP per capita, and then look at those correlations. And it's always the case that the correlation tends to be larger in the places that are more developed. And so that's going to be something, a force that is quite important in the model that I'm going to show you. Okay, let me show you some of the mechanics of it. So we're going to call two-dimensional surface S. Every location in that surface I'm going to call R, so a typical location. And again, in the application, that's going to be the 1 degree by 1 degree cell. And then you can partition, of course, that surface into countries that are just groups of these cells. We're going to keep population constant at 1 unit. And so in some sense, think about, every time I talk about population, you should think about the share of population in the world. It's not the actual number of people, but the share of population in the world. Okay, so what are the preferences of these individuals? So this is this equation. So now I'm going to use my pointer. So you have the utility of an agent that has a history of the locations where it has been, or where she has been, which I'm going to call R bar minus here. And then today is at location R. So the location where the agent is today is going to give the agent some utility, some amenity, which we're going to call AR. And this ATR is going to be determined according to this equation here below. So what is this telling you is, well, we're going to do it, there's going to be like a location fixed effect, if you will, in terms of amenities. So this is like the characteristics of the location that are immutable in the model. And then there is going to be a congestion force. So in the final calibration, this lambda is going to be positive. And so, locations that are very congested are not going to be locations that are as nice to live in. We're going to estimate this in a particular way that leads to that, at least at this level of geography. The level of geography, the level of resolution of the geography, of course, can matter for some of these parameters at the solution that we're going to be using. This object seems to be positive, which means that there's a congestion force here and through amenities, and is governed by this parameter lambda. Okay, so remember So I'm going to keep pointing to and emphasizing sources of agglomeration and sources of congestion. This is a source of congestion, this lambda, okay? And so this is how these amenities are going to be determined. Then there's a consumption aggregate that is going to be a CES as is standard with parameter rho. Then there's going to be these epsilons, which is your idiosyncratic preference for particular locations. And so you're going to have a realization of these epsilons, which is going to in part determine where you want to live. And so, you know, if you are in R, you've got a particular shock here that determines how much you like R. And then there is these mobility costs. And so all of these objects should be very familiar from the previous lectures. All of this should be well known, right? The new part is this last term. And so what is this last term? These are the mobility costs. So the fact that, you know, in order to get to R, you move several times from the different locations. And the way we're going to introduce this mobility cost is, you know, if I move from Mexico to the United States, you know, there's a cost involved in that move. But the way we're going to model that is we're going to assume that that is a flow cost, right? So I move from Mexico to the US and I keep paying, right? I keep paying because I'm not at home. Or I'm not, I guess this is my new home, but or not so new anymore. But I'm in, you know, not where I was born. And then, you know, if I move again, and if I move to Germany, then you know, I pay for that move as well. Okay, and I'm going to put some properties on these functions in a second, but just understand how this works. And so, you know, this is, you're dividing by objects, so therefore the -1, you're dividing by the multiplication of these flows of costs that you pay for every move that you make. You know, and it's going to hopefully become clear exactly why we model things in this way, because it's going to lead to this reversible cost that I was talking before. Let me just say one thing about these idiosyncratic shocks for a second. So, you know, the others have talked about them before. What's the role of this shock? So, you know, so people get idiosyncratic preferences. And so think about New York, right? So there's New York is a very productive place. It attracts lots of people. And of course, you know, if you're a New Yorker and you love New York, right? You're great, right? Because you love New York, and on top of that, you know, New York is a very productive location. So you're very lucky, right? But then, you know, New York attracts more and more people. And then, you know, the marginal guys that New York attracts, you know, they don't like New York that much. The reason they're there is because New York is a very productive place. And so they can earn high wages there. And so, you know, if New York wants to grow, right, it needs to attract progressively people that like it less and less there, right? And how much less and less, how many people there are at that margin, right, is governed by the distribution of these shocks, right? And in particular by the shape of the distribution of these shocks. And so when you make the distribution Fréchet, the parameter of that distribution, which I'm gonna call omega, capital omega here, becomes an agglomeration, is an index of how strong is that congestion force, right? How much more I need to pay in order to attract people, how dense is that margin there, or, you know, how the marginal guy that I attract, if I want to attract a certain number of people, you know, how much more do I have to pay them because the marginal guy now likes it even less there, okay? And so that's governed by this omega. And so omega is another parameter governing congestion, okay? So now we have two parameters governing congestion. We have the omega here and we have the lambda, okay? So keep those in mind. So here's an assumption on this mobility cost, these flows of mobility costs that I mentioned before. This is what I'm calling assumption 1. So if you move from R to S, we're going to assume that there's a component that depends on the origin, there's a component that depends on the destination, right? So it's separable in this sense, right? And that, of course, if you stay in the same location, you don't pay anything, right? So if you stay in R, you don't pay anything. So this is kind of, the second one is kind of immediate. The first one is a big restriction. One, for example, thing that it rolls out is migration costs that depend on distance, right? They can only depend on where you started and the destination, but it's not bilateral, right? Now it happens to be the case. The only thing that matters in the model, and as is going to be the case, is the number of people that are in a particular location, and not where they come from in terms of, in order to determine the evolution of the economy. Then this is enough this is enough for the model to explain exactly how people move across locations. So another way of saying that, and I said it in a slightly convoluted way, is if the only thing that matters is net migration, right? This is sufficient. This is, all the degrees of freedom that you require. If you care about gross migration, of course, this is not sufficient. Okay, so this is restrictive, but it's not restrictive in a model in which the only thing that matters is where people are, and not where they come from in terms of, for example, the labor supply. Okay, so then what is the agent's value? Well, an agent that starts in some location R0 that receives a particular vector of shocks in period 1 is going to get some value. I'm gonna group these terms here in the U, right? It's going to get this value in the first period, and then tomorrow, right, it's going to make a decision of where to go. So it's going to decide where to go in period 2, right? And it's going to get some utility there, and then it's going to get some continuation value after that. And so the agent, importantly, has to make it has to build expectations on this object here. Now, here is the important part of all these assumptions, in some sense, that I made, in particular this assumption about the fact that I can separate the M1 and the M2, is that, in order to make the decision of where I want to be today, I don't really care about this second part. This decision here doesn't affect this term, this second term. And so in that sense, I made the decision of where to go essentially static, or in practice static. That's the simplification that I was talking about before, right? And so that's, of course, key for tractability. Note one thing that is important here, which is these location endowment effects, right? So, the trick of this separability is then that I can bring out, this cost in my original location R0 out of this bracket, right? So it doesn't affect my decisions. So where I start from doesn't affect my decisions. It does affect the level of my welfare, but it doesn't affect my my decision. So that's key. But it does affect the level of my welfare, which is like this endowment effect, right? So if you happen to come from a place where productivity is very low and amenities are very low, maybe you can, move out of that place and create a better life for yourself, but you have to get out, and that's costly for you. You have to get out, right? And that affects your welfare, and that's this term here, right? Well, if you're lucky enough to be born in a wonderful place where you just want to stay there because it's wonderful, right? Then you don't have to get out, and so you don't have this term, or this term for you is larger. And so that implies that you are going to have higher level of welfare. Now, that's not going to affect your future, at least in this setup. It's not going to affect your future path, but it will but it will affect the level of your utility. And so that's in some sense this location endowment effect. Some people are lucky and get high utility, some are not so lucky. And get lower utility, even though, you know, they can get out of those bad locations eventually. You know, and so the expected utility, you can calculate the expected utility here is not exactly going to equalize because it depends on these migration costs, but you can, you can essentially do the same type of calculations of what's the probability that people are going to choose a particular location relative to another that, you know, we do in the standard spatial quantitative models, and that you've seen, you know, you've seen Steve do, you saw, I guess, Dave do. I mean, and all these models have this structure. And so the share of people that are going to be in a particular location, where this H is the amount of land available in a particular location, which is not always the same, even though these cells are one by one, because, you know, the world is circular, first of all, but second, you know, there's coasts and there's seas and there's rivers and stuff, and so we want to take that into account. So, but the share of people in the different locations is just going to be given by this expression, where this U is this aggregate of the amenities and the consumption basket, but it's also going to depend on this mobility cost. Okay, so that's the agent's problem. And now let's go to the firm's problem. And so that's where this endogenous investment is going to come in. And so, you know, the production technology is going to be Cobb-Douglas in land and labor. And what I'm going to do is I'm going to divide everything by land. So everything is going to be in terms of units of land. Okay. And so production in units of land is going to be given by this expression here. And so what is this expression? Well, because because technology is constant returns in land and labor, right? But I already put everything in terms of units of labor, right? This is labor here. Let me see if I can write here. This is labor in terms of units of land, right? And this exponent is the share of labor in the production. 1 minus mu is the share of land in production, right? And so that it adds to the constant returns Cobb-Douglas. But the fact that that mu is less than 1, because land is a factor of production, implies that there's going to be decreasing returns to scale in units in a particular location. So conditional on the amount of land in that location, which again is a congestion force, right? Why? Because if I keep piling production in a particular location, then, you know, the firm, conditional on the amount of land in that location, the firms are going to face decreasing returns. Okay, and so that's given or governed by that mu parameter, or really by 1 minus mu, which is the share of land. Okay, the first two terms here, right, denote productivity. Those are the productivity terms. Let me talk about the second one, the Z, first. So the Z is your standard productivity draw for the firm that is going to come from a Frechet distribution. And so it's going to determine how productive is a firm in producing variety omega in location R, right? Which is going to come from, it's going to be random. The first term is more new. The first term is an innovation term. So the firms are going to decide, well, how much do I want to innovate, right? And what innovations do is they shift, in some sense, the distribution of shocks that these firms are getting. So they're shifted today by multiplying it by this term here, right? And they're going to shift the distribution from which you're drawing in the future in a way that I'm going to explain in a second. And you have to pay for that. And how much do you have to pay? You're going to pay this amount here. So you're going to pay whatever you want to innovate raised to some power psi. Okay, and so it's costly to innovate. This is the cost in terms of units of labor that you have to pay, but that increases your productivity, and it increases your productivity according to this parameter gamma 1. And so gamma 1 and the psi are parameters that are going to determine how easy is it to innovate in a particular. So in particular, if gamma 1, there's going to be decreasing returns to local innovation. So okay, so that's that, and so these firms are gonna draw from this distribution. It's gonna be a Frechet distribution, and the level of this distribution is gonna be governed by this parameter, this t, or this function t here. It's gonna depend on the location, and we're gonna add, this function t is where the dynamics are gonna come. So first of all, we're gonna add some static agglomeration effects that people have talked about during these lectures too. If there's more people in a location, their productivity in that location is going to grow because of a static agglomeration effect. And that static agglomeration effect is going to be governed by this parameter alpha here. So that's, a well-known type of effect. But more importantly, if I innovate, if I'm a firm and I innovate, that's going to, matter for future draws. I'm going to, those innovations essentially are just shifting the distribution of draws, right? And so how does that work? So think first about setting this gamma 2 to 1 so that this term in brackets is not there. So if you eliminate these terms in brackets, this tau, which determines the t, right, is this object here, is, well, whatever you innovated, this phi, right, and is determined by that, and is determined by your previous tau. So that's the dynamic. You're shifting by choosing your innovation, the tau, right? So that's just what I was saying. You're shifting the productivity. You're shifting the productivity in the future, and you're shifting the productivity today through this. And these two are consistent. Both are raised to the gamma 1. The fact that one is raised to the theta is just coming from this Frechet distribution. The second term here in brackets, it's a diffusion effect. So what is that? It's telling you, look, if you're in certain places where there's really not that much innovation, you still get to use a cell phone, you still get to use a television, you still get to use innovations that others have invented. And by using those innovations, you can, in some sense, use them to innovate locally yourself as well. Maybe not at the same level as those places, but you can do something yourself. You don't need to start from zero, right? And so that's this term here. And it turns out, as I'll explain later, that this is actually crucial in order to have a unique equilibrium. You need some of this diffusion in order to not actually to have a unique balanced growth path. So this is going to be important to get that. Okay, let me erase all of this. And so that's the technology of these firms. Let me say this, and then maybe I can take a couple of questions. So this is the technology that the firms face. It's like I showed you, dynamic, but the basic logic that I explained before is going to apply in the sense that because technology diffuses locally, and firm profits are linear in land, and they compete in prices. Firms are going to be competing for land. There's all these entrants that want to enter and they want to produce in that location. And so land rents are going to eat up all the profits because land is the one thing that you cannot replicate in that location. And so, everyone wants to produce in Midtown Manhattan, right? Why is Midtown Manhattan what it is? Well, everyone has been investing there for a long time. I want to go in there, right, as well. Now, the firms that have invented, that benefit from being in Midtown Manhattan, they want to protect, of course, being there. They want to keep staying there, but they now have to compete with me. I want to enter there, and I want to take advantage of what Midtown Manhattan has become. I didn't create it, right? But I want to take advantage of that. And so who's going to benefit from that? Whoever is the landowner, because the landowner is deciding who's going to be, at the end of the day, producing that. And so what does that mean? It means that, tomorrow and the day after tomorrow, all the profits that come from these innovations are going to be, from the firm's perspective, zero. Of course, the economy as a whole is going to benefit from that, and certainly landowners are going to benefit from that. But for the firm is going to be zero. And so so what is the firm going to do? Well, the firm is going to face essentially this problem here, which is a static problem where the firm is deciding how much to innovate in order to win the competition for land in that location today. So the firm's importantly, even though there's perfect competition, the firm is going to innovate, right? But it's going to innovate optimally, right, to maximize the bid for land that is going to, advance, and then whoever gets the highest bid for land is gonna win that location. Okay, and so that's gonna solve the innovation problem. And now, but it's very simple, because now essentially we can solve the model forward and the problem of the firm forward, rather than having to go to some sort of steady state or balanced growth path and solve the problem backward. Okay, so the rest of the model is pretty standard. There's a trade, and the trade subject to transport costs that are bilateral. So these depend on the origin location and the destination location. We're going to assume trade balance location by location. These are long-term models, so we don't feel too bad about that. And so that's going to lead to a structure that leads itself nicely to be analyzed and to be computed, or to be put in the computer and do different sets of counterfactuals. Why don't I stop here, get a couple of questions, take the break, and then I can continue.
Fantastic. Thank you very much indeed. That was fascinating. So we've got a few questions in the box here. The first, which has received a lot of upvotes here, is does the choice of which simplifications of the full spatial dynamic framework that are most useful or harmful for modeling agglomeration depend on how we microfound agglomeration? And related, can the addition of dynamics inform our understanding of the relative importance of different mechanisms?
Yeah, I mean, that's a wonderful and very hard question to answer. I mean, I think so. I mean, I think we have evidence on the evolution of locations over time, and maybe we can use some of that evolution together with models that introduce particular forms of agglomeration in order to try to identify some of these dynamic agglomeration effects. Now, it's going to be important. The word dynamic agglomeration effects is very important in the sense that it has to be something that depends crucially on the dynamics. For example, like this type of mechanism that I was talking about, where people come, as a result of people coming, market size increases. As market size increases, people innovate more. And so there is this dynamic agglomeration effect, and that dynamic agglomeration effect has certain implications. And so whether we want to have it or not depends on whether those implications are, at the end of the day, present in the data, or we can find them in the data. And I think the fact that we see these correlations across locations that I was talking about tells you that it's a good candidate, at least. Then the more micro foundations of these agglomerations, whether they are, which one of the Marshallian effects is the right one, is there, or more important, labor pooling or externalities, etc. It's not obvious to me that at least these frameworks at the level of detail that they're done right now can be very helpful with that, because of course you have to deal with the fact that the economies and locations are receiving shocks over time, etc. So things are a little bit hard to identify over time. And so I don't think we're really at that level, but I mean, I wouldn't say no. I'm sure someone may be better than me at figuring out some identification tests for static agglomeration effects that relies on the evolution of the economy, but we don't have that right now.
Terrific, thank you. Maybe in the interest of time, we'll just ask one more. So there's a question here about spatial heterogeneity and industrial composition. So in particular, whether the TFP growth map that you showed towards the beginning of your presentation controlled for this, and whether you could talk a little bit more more generally about spatial heterogeneity in industrial composition here?
Yeah, so I think spatial heterogeneity, industrial composition, and occupational composition is both crucial and important for dynamics, partly because the cost of innovation and these agglomeration effects and market size effects, etc., are going to vary dramatically across industries, or we think that they vary quite a bit across industries. And in terms of occupational composition, because they also affect different people with different skills and different occupations differently. So yes, I mean, absolutely. But David Nagy in his dissertation introduced the model with two industries, a dynamic spatial model with two industries, agriculture and manufacturing. It's not an easy thing to do. So that's, and so again, it's in the agenda. We need more. I think we understand fairly well the sorting in space in static models by now, but we need to introduce it in these dynamic models, and I think we need to do more there, but we haven't yet. I mean, so again, opportunities.
Great, thank you very much. Well, in the interest of time, we will stop the questions there and hopefully have some time for some more of the others at the end of the talk, but we'll just take a 2-minute.
So, okay, so we build this structure, and that's kind of all the elements of the model that I was wanted to describe. Now, it turns out that we chose the structure of the model, and in particular all these power functions, in a detailed way. This is also following some of the logic of Allen and Arkolakis, in order to build a model where at the end of the day, the static part of the model boils to a system of equations that look like the system that I have here. And so this is a system of equations that depends on local productivities, depends on the amenities in the different locations, right? Which at a given point in time are going to be determined, right? Depends on the amount of land in the different locations. And then, you're solving for the amount of people in all these different locations. So it's a system of equations, nonlinear system of equations in LT. And so Treb and Constance, in their paper, they used a set of theorems by Sabretko and all in order to solve systems of this form. And we can use that machinery here as well, and to prove the following results. And so so let me briefly go over them, because I think they're illustrative of what's happening in the model. So the first one, what I'm calling lemma 3 here, is that the equilibrium exists and is unique, and if this condition is satisfied. Now, look at this condition, and if you remember, I know it's after the break, but maybe you still remember the different agglomeration forces and congestion forces that I pointed to before. So look at the right-hand side of this equation. So these are the agglomeration forces, right? The one on amenities, the fact that land was an input in production, and the idiosyncratic preferences for the different locations. So these parameters, right, have to be larger than the parameters that govern the agglomeration effect. So this is the agglomeration effect that comes from the fact that there's a market size effects in innovation, and so you want to innovate more when there's more people there. So that's the static effect here that is governed by the gamma 1 and how costly is innovation, which is governed by the psi. And then the static agglomeration effect, the static spillover that I added in the determination of the level of the distribution of productivities, right? So the left-hand side are the parameters that govern the agglomeration effects. The right-hand side are the parameters that govern the congestion forces. And what this is telling you is if the parameters governing the congestion forces are larger than the parameters governing the agglomeration effects, then the equilibrium is going to exist and is going to be unique. And not only that, if this is the case, you can solve this system of equations using a simple iterative procedure that is going to converge to the unique equilibrium. And so this is fantastic, right? Why is it fantastic? Because it tells you that as long as this condition is satisfied, we know how to solve this model, right? For whatever number of locations and whatever heterogeneity across these locations, etc. Right? And there's going to be one unique equilibrium that does so. And so this really kind of lends itself to analyzing, in the sense that, you know, it gives us a lot of tractability for computational tractability. Okay, and so and this condition is, like I said, very intuitive as well. You know, I think in some previous lectures, people talked about, you know, the new economic geography and some of the logic in the new economic geography. And the new economic geography was all about finding ways of creating agglomeration. And what this condition tells you is, in some sense, or it's at the core of this different approach, this different quantitative approach, which says we don't want to create endogenous agglomeration. Agglomeration is going to be the result of these differences across locations, right? What agglomeration forces are going to do, they're going to just emphasize those initial differences. They're going to enhance, if you will, those initial differences. If you invert this condition and you make agglomeration forces actually larger than the congestion forces, then you're going to start getting multiplicity. Then you're going to start getting endogenous forces of agglomeration affecting the distribution of economic activity. And this is related in the literature to what sometimes is called the no black hole condition. So that would be so this is kind of a no black hole condition, or is related to this no black hole condition in that literature. But it's very simple, very nice. Congestion has to be larger than agglomeration, right? So that's an equilibrium. The other question is, you know, the balanced growth path. So this economy is evolving, right? And the distribution of economic activity is changing over time, right? But eventually, you know, in principle, it can stabilize and it can converge to a situation where the distribution of economic activity is stable, it is not changing anymore, but the economy is still going to be growing overall because there's still innovation. It's just that, you know, that distribution of population in space stays the same. And so what's that condition? What guarantees that there's a unique balanced growth path? Well, is this condition here. And so this condition, if you remember the one I just showed you, is exactly the same. So on the right-hand side, you have the congestion forces. On the left-hand side, the first two terms are the agglomeration forces. The third term, though, is new. And so the first thing it tells you, well, you know, it's a little bit harder to satisfy this condition because now you have an extra term, right? But second, remember this 1 minus gamma 2. This 1 minus gamma 2 was the term that governed how important was the diffusion. And what this is telling you is it better be the case that gamma 2 is not equal to 1, otherwise this condition is never going to be satisfied. And so what that tells you is that it better be the case that there's some diffusion, right? If there's no diffusion whatsoever, right, there's some areas that are going to fall behind completely, and that then involves that some places are going to be completely left behind. And what those places are and the particular configuration of these places can vary and can be different in different paths. And so if you want the system to have a unique balanced growth path, then you need this condition to be satisfied. In the calibration that I'm going to show you, you know, it is easily satisfied. So that's you know, so everything that I'm going to show you is going to have these features. Now, in the balanced growth path, you can look at growth. So in particular, growth in this ratio of use, or in consumption, and that growth is going to be proportional to this object here. Now, of course, these L's are endogenous, right? But this is just like some average, right? Some like a weighted average of these L's to some power, right? And so what this is telling you is growth in the balanced growth, growth in the balanced growth path. So it's going to be determined by the distribution of people. So that's the link exactly between growth and the distribution of people. And, and it's, of course, for example, going to depend on what are the locations that are feasible to produce. And so that's where, these applications to climate change or coastal flooding, etc., matter, in the sense that if I change the locations where you can produce, say, because some are flooded, then that's going to affect long-term growth through this. Okay? So that's the structure of the model. So now let's try to quantify it. And so this is a whole topic on its own, and I don't have that much time, so I'm not going to spend too much time on the calibration or estimation of the different parameters. There's of course a paper if you want to do to take a look. Let me say a couple of things. First, just as a summary of the way we do things. The first thing is that this model, conditional on productivity and conditional on amenities, right, determines the distribution of population and the distribution of income across locations. Now, it's also the case that if I have the distribution of income and the distribution of population in the data, I can invert the model, and together with some notion of welfare in the different locations, I can actually recover those amenities and those productivities, and I can do so uniquely. And so we're going to actually do that, and that's of course conditional on parameters. Then we need transport costs. Transport costs, we're going to use the fast marching algorithm, and so we're going to do the optimal routing and adjust parameters so that the model satisfies the gravity equation. And then finally, we need the migration cost. And so what are we going to do with respect to the migration cost? We're going to calculate them such that the model exactly predicts net migration between 2000 and 2005. So all the calibration is going to be for 2000, right? We're going to run the model to 2005, and I'm going to ask the question, well, is the model hitting the levels of population in 2005? And I'm going to choose these M2s, these migration costs, so that the model does so exactly. Okay, so in that sense, I'm inverting those costs as well. Okay, and so in that sense, the model is predicting exactly those by choosing, because it has enough degrees of freedom, those migration flows. And so then I can do exercises with migration costs. I can, shut them down and say, well, there's no migration cost whatsoever, or I'm going to reduce them by a certain proportion, etc. And I'm going to do that by using this Greek letter here that I forgot the name. Okay, so what is the outcome of that? The outcome of that is, first of all, from that inversion that I talked about, we get some fundamental productivities in different areas of the world, some fundamental amenities in the different areas of the world, the moving cost in the different areas. And so, look at fundamental productivities, high in the US, high in Europe, high in Japan, high in some parts of the Middle East because of oil, the big cities light up, etc. So this all looks fairly natural. These are the amenities. Think about this as fundamental amenities. So this is how good these locations are in order to live there, right? And so, I guess they are what they are. They are low in the very cold regions, for example. And these are the moving costs, so how costly it is to move into the location. So the M2, remember, there were two costs, M1 and M2, but because we had that if you stay in the same location, you don't pay any cost, that, you know, one is related to the other. So the only real variable that we needed to get was M2. And this M2 is how costly it is to get into that place, right? To move into that place from wherever. And so you can see, you know, it's very costly to move to the very northern regions there. So it's not only, clearly, it's not only about, you know, getting a visa or something. It's more about how costly it is to go live there and adapt there. And so how is the model determining that? The model is determining that because it's saying, well, lots of people should be moving to some of these places, right? Given the characteristics of these places, I don't see that. So it must be that it's costly to move into these places, right? And so this is the result of that, okay? And so, you know, so our baseline is going to be for the year 2000. And from the year 2000, I'm going to kind of let them all run. So this is the economy as in year 2000. This is coming from the data. And then, you know, this is, once I let them all run, like I said, this distribution is varying over time, is changing over time. In fact, there's very protracted changes in the economy over time. But, you know, this is always a little bit surprising to me, the fact that you have this geography. I mean, the geography of the world is very complicated, right? I mean, in the world, it has all these specific patterns, etc. And somehow, you know, there's this distribution. This distribution, you know, is changing, and some areas are developing. As a result of those areas developing, some other areas are developing, etc. And so the changes are all happening, but eventually that distribution stabilizes, and in fact is guaranteed to stabilize because there's only one balanced growth path, and you get this, and this is the distribution that you get as a result. Okay, and so what's happening in, you know, this very long-term future? What's happening is that, you know, lots of people go to this area of the world. So many people live, you know, go away from, you know, the standard hubs in the developed world. Today, they go and as a result, you know, in the long-term productivity in those areas is high. Productivity stays high in Europe, stays high in some parts of the US, but, you know, it becomes very high in China, in India. But you know, but utility is not that high there because, you know, people are very agglomerated there, etc. And so at the end of the day, you know, some of the developed areas in the world, they stay, the welfare there stays higher, even though they don't become the centers of production of the world. Okay, so, and here is real income per capita. You can see real income per capita also growing along in this region around China and India. So, but this is happening in the very, very long run, right? So this is between 200 and 2600. You know, the first thing that I mentioned is you start with this negative correlation between income per capita and population density. This is the data, right? The minus the point where you start from in the data. And then what happens in the model is over time, you know, this correlation starts growing. So focus on the blue line, that's the one with current migration cost. And eventually it grows and it's pretty high, right? So close to the balanced growth path, the correlation is close to 0.6. So people are really where population density is high wherever people are, right? Why? Because slowly but surely, people make the places where they are more productive, okay? And so, you know, that leads to this curve. And you can see the effects on the growth rate of productivity. So growth rate of productivity first goes down a little bit and then kind of recovers over time until it converges at the level that is slightly higher than the level in 2000 where we initially calibrated the model. And then the other two curves are what happens when I relax mobility restrictions. So free mobility is the the orange dotted line, and then some intermediate case is the green line. So you can see how, what happens if I allow people to move freely right away. Immediately this correlation jumps. Why? Because of course people want to, immediately move into places that have very high productivity. And so, eventually that correlation keeps growing, but, it jumps right away when I let people move as a result of relaxing some of these migration costs. And that, of course, also leads to higher growth rates. So, and so this is the effect that I was talking about on how spatial frictions can affect the long run growth rate of the economy. And so this is, you can say, well, this is about, this is not too big of a change. It's about 0.5% per year. But, of course, that accumulates over time to very big level differences in the scenario with free mobility relative to the current mobility restrictions. So, this model has a lot of bells and whistles, of course. And so, one thing that we were interested in is to say, are we getting just some, crazy predictions here? And has this anything to do with what we've seen in terms of the evolution of economic activity and mobility of people over time? And so the exercise that we came with in order to try to show that some of the predictions of the model and some of these fundamental forces that we're trying to model are relevant was this backcasting exercise. So what this backcasting exercise does is it turns time backwards. So it starts from 2000, right? That's the information that the model is using. And then it says, well, let's try to predict, or let's try to look at what's the population that the country predicts in the past, right? And so, the prediction, the model can predict backwards the same way it can predict forward, right? And so this is this exercise. And so we're running the model backwards, and then we're going to compare the predictions in terms of population with this is country population, in the past. And so these are, you can see, these are the correlation between the model and the data at different points in time. So this is 1990 and so on, all the way back to using Madison's numbers in the late 1800s. And so you see the correlation. So first of all, the correlation is obviously very large in levels. Now you can say, well, the reason you're doing so well in levels is just because people don't move that much, right? And so you're naturally gonna do well in levels. And so what we have here is the correlation in changes, right? So these are changes in population, and this is the correlation in changes. And so you see that the numbers, vary between 0.4 in 1990, all the way to 0.74 in 1950, and even 0.34 in 1870. And then now we're talking about the correlation in changes, right? So these are the changes. And so what do we conclude from this? What we conclude from this is, well, the model, these fundamental forces in the model have a lot of predictive power in terms of these long-term movements in population. Remember, you're getting, so if at the end of the day, your correlation is 0.34, there's a lot that happened between 2000 and 1870 that has nothing to do with this model, right? And that has to do with all sorts of political events, etc. That of course there's no chance that this model could ever explain, that there are specific shocks that this model is not designed to address or explain or anything. This is only about the fundamental forces, that we're bringing in to this economy. And it's only using data from 2000, right? There's no dynamic data that we're using from the past in order to generate these numbers. And so we think that, what this shows is that some of these fundamental forces are kind of interesting. So these are some of the exercises that I talked about with free mobility. Let me jump across, then you can take a look in the slides if you're interested. There, of course, in the paper. Let me just stop at this table. So this table shows for these different mobility parameter that, you know, remember I was raising these M2s, these mobility restrictions, to some power. If I raise it to 1, that is the you know, the economy as is. If I raise it to 0, then I make them all 1, and so there's no migration cost. And these are the gains in terms of real income, discounted utility, and the migration flows that they would imply if you were to change this at impact, right? So this is the migration flows at impact. And so, you know, in general, the model generates about 3% or 0.3%, sorry, I should say, flows, net flows in the world. That's about right with the data. You know, if you make this 0.75, so you reduce kind of these frictions by 25%, you make 21% of the population move, and you have gains in terms of wealth for about 60%. If you know, just as a thought experiment, of course, you can undo this. You were to eliminate all these migration restrictions, you would, you know, increase welfare by 300%, move about 70% of the people. And of course, the evolution of the world would be quite different. The fact that these numbers are so large, of course, has to do with the fact that, you know, the economy, this is affecting growth rates. And it's not only affecting growth rates, it's also making people, you know, be productive wherever they want to live, in places that are nice to live. So it's making the distribution, once you relax migration restrictions, is making the distribution of amenities more consistent with the distribution of productivities. And so that it's also very good for welfare. So that explains the big difference between the welfare impact of reducing migration restrictions and the discounted real income impact of reducing these migration restrictions. Okay, so, you know, just as in the last few minutes that I have, let me just mention this application of this framework that we have to coastal flooding. And so this is joint work with David Nagy and Klaus Desmet as well, but it's also we joined forces with some of the experts in the world on flooding and sea level rise more generally, and also, you know, coastal elevation. So people that study, you know, and have models of exactly, you know, what's the elevation of the different coastlines. And they gave us essentially the data about, you know, projections of flooding over time that we're gonna incorporate into the framework that I just showed you in order to try to evaluate what's the impact of coastal flooding, taking into account the fact that this is a dynamic effect. Now, one thing that is very important to understand when you understand flooding, when you think about flooding, let me jump through some of these, sorry, is, you know, there's a projection of how much, you know, sea levels are going to rise. There's a calculation of what's the coastal elevation, and so that tells you something about what, you know, what areas are going to be flooded. But, you know, a good way to think about this is not like the bathtub type of model where, you know, sea levels rise and then everything is going to be, you know, all the coastal sea levels are going to rise by exactly the same amount everywhere. That's just not true at all. There's a lot of spatial variation in the sea level rise. And so we're going to take that into account, right? And, you know, this is also, you know, scientists are not exactly sure about what's going to happen. And so, you know, there's different scenarios of how severe that is going to be. And so this is average elevation in the different scenarios. So on average in 200 years, it's going to be about a little bit more than 1 meter, but, you know, there's a lot of variation. So what I'm going to do is I'm going to use all these different paths, look at the land that is going to be flooded, essentially take that out, right, and recalculate my economy without that land, and then calculate the losses implied by that in this model, taking into account all the different forces that we've been talking about. And if you do that, this is what you get. So this is again time on the x-axis. On the y-axis, I have real GDP, and these are the cost of the flooding in terms of real GDP. And so you can see how the cost of the fact that a bunch of locations are going to be flooded is going to rise to about 0.5% of GDP in about 2130, right? And then it's going to decline back to zero. And you can see kind of the confidence that you have on that based on, you know, the different paths that the science. So this is all coming, this uncertainty, if you will, is all coming from the fact that scientists are uncertain as well about what exactly is the path that the economy is going to follow. But you can see that it's also going to have this hump shape kind of shape. Why hump shape? Well, you know, flooding is going to first increase, and so that implies that the costs are increasing. But then eventually, you know, people are going to move to Chicago, I guess, from New York to Chicago. And once they're in Chicago, they agglomerate Chicago and they, you know, make Chicago larger and create a life there that in some sense is not longer affected by flooding, assuming that Lake Michigan doesn't flood. Maybe Chicago was a bad example, but anyway, Denver, and so you know, they move there, and once they move there, etc., they start agglomerating there. They create new cities, they create new places, and to the extent that they do so, you know, they are less subject to increases in flooding, and that matters for the cost. And so that's why you have this decline over here. So this is the population that is going to be displaced relative to the case without flooding over time. That doesn't have that shape, but welfare does. Okay, so that's some of the costs. Let me, you know, I'm gonna jump through some of that and, you know, try to explain this graph, and then I'll take some questions and conclude. Okay, so you see what we're doing. We are trying to estimate the cost of coastal flooding by understanding what areas are going to be flooded. Once we know what areas are going to be flooded, we know, you know, which areas you cannot produce in, so people have to move and they have to adapt and they have to, you know, locate somewhere else. And that adaptation process, in some sense, is crucial, right? This dynamic adaptation is crucial to understand the effects. In some sense, in some sort of basic sense, you can think about economics and what we do in general, modern economics, as just modeling adaptation, how agents react to things, right? And try to model that adaptation in a careful way. And so with climate change, we want to do exactly that. And that's something that in some sense scientists have not really done. We want to model the adaptation that is going to be the result of these climate shocks. And so look at this. So the blue line here is the median scenario that I just showed you, right? So that leads to about 0.5% in 2130 as a maximum loss from climate change. So that's, you know, just that average. Now look at the role of adaptation. I'm going to show you the role of adaptation by eliminating some of the channels of adjustment that are present in the model and that, you know, we think are important in reality. So the red line is the case where you do like a naive calculation where you say, okay, let me take where people are going to be today and in the future according to the model, and let me just say that all that activity, you know, is going to disappear. And so this is kind of the way a lot of these calculations are actually done. So that is naive in the sense that you don't take into account that people, you know, are going to stop going to those places if they, you know, are likely to be flooded. And so of course, then look at the costs. The costs are going to be, you know, a lot larger. So they're going to be 4.5. They're going to be 4.5 of GDP rather than what they're actually going to be according to this model. You can also eliminate, you can also keep population fixed. So don't even think that population is going to move, just keep them where they are and eliminate that part of GDP. That would give you the yellow curve or the green curve if you don't have the fact that they are going to move somewhere else. And then once they move somewhere else, they're going to start innovating and, improving the locations where they are. And so these are big differences in the cost. And this shows you exactly how important it is to think about adaptation and how people adapt to this type of climate shocks, but any other shocks. And so essentially, again, this is what modern economics is about. It's about modeling adaptation. So in particular, when we think about climate change and this type of climate shocks, it's very important to incorporate some of these effects. So, you can then study local effects and how this affects the different parts of the economy. The paper goes through all of that in literature in detail. Let me just then stop here and just take 1 second to conclude. I hope I was successful in showing you that, this is an exciting area of spatial economics. There's a lot we don't know. There's a lot of theory that we still need to develop. There's a lot of quantification that we need to do better, more careful. But we have some basic structures that tell us something, that have made a lot of progress, and that show kind of, in some sense, the potential of this area. It's important. The key, the golden standard is, and what we're still, don't have, is a spatial framework that has the anticipatory effects, but also has consumption savings decisions, capital accumulation, and innovation. So for all young people out there, jump in. This is an exciting area to work in. Okay.
Thank you very much indeed. That was wonderful. We've got a couple of minutes, so we'll try and squeeze in a couple of questions if we can. There's a few in the box here. So the first question, which has received a lot of votes, is given market size effects are strong here, does the total population size affect the aggregate long-run growth rates?
So that's a good question. It's not immediate in the sense that the distribution matters as well, right? So yes, in principle, total population can have an effect, but because population is distributed in space, think about if at the end of the day, you're just replicating a city that is just like the other cities, then you're gonna have a growth rate that is exactly the same as the previous growth rate. So that's, again, the argument that I was making at the beginning. The size distribution is kind of balancing the increasing returns relative to the constant returns. And so this is very much consistent, even if population is growing, with growth rates that are constant, that are not growing, because you're using areas of the world where that you were not using before.
Fantastic. We've got about 30 seconds, so I'm going to squeeze in one more and then we'll quickly go to the outro, which is, can we view pressure shape parameters as a fundamental, or is this a function of other unobserved and potentially endogenous or potentially time?
Sorry, can we see?
Omega, so the pressure shape parameter, or is it a function of potentially time varying technological or economic factors?
Look, I think as a matter of principle, everything is a function of some process that led to it. And so in principle, you can bring dynamics to all of these parameters. And in principle, we can incorporate many dynamic channels through some of the parameters, through all pretty much the parameters that I kept fixed. But we have to choose our battles. We have to choose the areas where we think endogenizing things and allowing for adaptation is most relevant. Is that the first place where I would go? Probably not. But again, it's based essentially because I don't know what is exactly the piece of data that I'm not able to address with this that I would be able to address with a model that has that endogenous component.
Fantastic. Thank you very much. We're 1 minute past. So with that, I will hand back over to Daniel. Thank you.
Esteban, thank you very much for this fantastic end to this lecture series and for taking us far into the future to the year 2600. That is super impressive. With that, we're coming to the end of this lecture series. I look forward to seeing some of you in the PhD student workshop in September. We've received 76 applications for that, which is wonderful and which we are evaluating at the moment. With that, I wish you a wonderful summer.